Yeah, thank you. So yeah, I will talk about a research project that was finished right when I started working here at IBS, when Attila Jo was visiting us for a couple of weeks. And it's a project about infinite digraphs. So I will give you a bit of background on this question, then tell you what we show, present you a couple of lemmas for the moment without proof, which will be sufficient to prove the main theorem. And I want mainly to convince you that if you believe the lemmas, then the theorem actually is correct. And then I will try to give you an idea how to prove these lemmas in much less detail. Okay, if you have any question at any time, feel free to interrupt me. So I can modify the length of the talk depending on how much detail I go into the lemmas. Okay. So first of all, let's talk about connectivity in infinite digraphs. So of course you all know Menger's theorem. And let me restate Menger's theorem in a digraph, in a specific digraph variant for you. So let D be a digraph. And let V and W be vertices of that digraph. Then the maximum number of disjoint VW paths, so by that I mean paths directed from V to W, is equal the minimum size of an VW separator. So take a set of vertices of the digraph not containing V or W in this context, such that every VW path contains a vertex from that set. So this usually slightly varies from standard formulations of Menger's theorem, where you talk between paths between two sets, but these variants are easily seen to be equivalent by subdividing every outgoing edge from the vertex V and every incoming edge from the vertex W, deleting V and W, and then consider these two sets instead. But there's a reason why I give you this formulation. Okay, so this is a theorem about finite graphs, which I'm sure every one of you knows. Even if you didn't study the directed version, its proof is basically very similar to the undirected version. Just need to be a bit more careful. So what are now the problems when trying to generalize a theorem like this to infinite graphs? So, of course, when we say here maximum number of disjoint paths, or the minimum size of the separator, what does that now mean? So, of course, we can just talk about cardinal numbers if we like, right? So, so basically, when we say, oh, if a maximum sized set of paths is, say, countable, then we also want a countable separator. But a theorem like this is kind of boring. So why? So the idea is whenever we have a maximal set of disjoint paths, all of these paths are finite. So if that set is infinite, then we can just take the union of all the vertices on those paths and we'll get a set of the same cardinality. And by the maximality of the set of paths, just inclusion-wise maximal, now every path needs to meet one of those vertices. So a cardinality version is trivially true and doesn't give us much information. So Erdős observed this and said, this is the wrong question to ask. And he asked what he considered the right question. So let me draw a bit. So if we have V and W here, and a system of disjoint or internally disjoint, that's what I probably should have said there, internally disjoint VW paths, then of course one direction of Menger's theorem is the easy one, right? So of course a separator needs to contain a vertex of each of those paths. Otherwise there would be a path that we don't meet. And in the finite case, this means of course so the other direction then gives us that each path needs to contain only one vertex. And this is the kind of structure that that Erdős said should be the thing that we want to look out for. So Erdős conjectured and much later Aharoni and Berger proved that there always exists a set of VW of internally disjoint VW paths, which I from now on call VW path system. So not always have to say internally disjoint set of internally disjoint paths. And VW separator, which are so-called orthogonal to each other. Where, what does that mean? So each path contains exactly one vertex of the separator and the separator contains no other vertices. So, and we now call path systems and with these properties, so for which there is such a separator, Erdős-Menger path systems, and these separators for which there is such a path system, Erdős-Menger separators. Okay, so this is so this was proved in published in 2009, which took a long time to do, and is very, very involved and non-trivial proof. So, so actually, I believe the published version does contain some technical errors which don't seem to be easily fixed. But all the experts believe that in spirit the proof is true. There just doesn't exist a full published version. But a couple years earlier, Aaroni proved a countable version of this theorem, which is much easier and is only a like 3-page proof, which you can read in Diestel's book if you're interested. So this is actually a quite nice proof, not that complicated. And today we only consider countable graphs, so we can rest assured that everything will work with regards to this theorem. Okay, questions so far? Oh, yeah, they actually proved the edge version. So I lied. And the vertex version is the consequence of the edge version. But yeah, and of course, all these other versions of having a vertex set here, vertex set there, all these work. Okay, so now what is our goal today? So in a digraph, we want to find a kind of global substructure and let's say in a rooted digraph, which witnesses the local connectivities exactly. So, what do I mean by that? Sorry?
You mean rooted here?
Rooted, I mean I pick a specific vertex which I call the root of the digraph. Okay, so this leads us to the notion of vertex-flames, or flames. So, definition. Vertex-flame, and from now on I will drop the word vertex, and just say flame, is a rooted digraph F with root R such that for every vertex of F other than the root, the ingoing edges in that digraph of that vertex is the set of final edges of an RV path system. So, so here we have our root R, here we have a vertex V, and I want that all the ingoing edges here, all of them, are on a path system from the root to that vertex. So every edge in some sense is necessary to witness the connectivity in that digraph.
internally disjoint.
Yes. Whenever I use the word path system now, I mean a set of internally disjoint paths.
So this doesn't exist in a finite diagram.
Oh, of course it does. I will get to that. So a flame itself now. I don't haven't said anything about substructure yet, but of course, what I've drawn here basically, just this would be a flame. This digraph itself. So it's true for this vertex because I just drew the path system, and for every other vertex, they only have one ingoing edge. So I just need to find the one path, and there is no other path to that vertex. I don't care about the outgoing edges. Yes, only about the ingoing edges. And the second definition, a subdigraph L of a digraph D is large if, again, for every vertex of D, and I should maybe say a spanning subdigraph, if for every vertex D other than the root, and let's say of a finite digraph for now, before we modify the definition. For every vertex other than the root, what would I want to say? The maximum size of RV path system in L and D are the same. So so the subdigraph doesn't destroy any connectivity, local connectivity from the original digraph.
Yeah.
Yes, the number of paths in the path system. And now we have Abel Prize winner Lovász, who proved, who proved in, I think, 74, is it? 73? Every finite digraph contains a large flame. So one note maybe, he didn't call these subgraphs flames. That was somebody else, because only a couple years later, this guy, no, let's write him correctly. So in 78, he independently proved a slightly stronger result, and he coined the term flame. He proved that every maximal flame in a finite digraph D is large. maximal meaning inclusion-wise maximal. And of course, the empty spanning subgraph is a flame. So now you know a flame exists, then you can take a maximal one in a finite graph. That will be large, so it implies Lovász's theorem. For any root. I mean, it's a statement about all rooted digraphs. Yeah, so.
You just said an empty digraph is a flame?
Yes. It's not large, but it is a flame. A set of ingoing edges for every vertex other than the root equals the number of directed paths to it, namely 0 and 0. Okay. What we try to do now is generalize these to infinite graphs, as is something that we like. And the definition of flame, as I gave you, is already one that we now can work with. Just because I phrased it carefully. But now the definition of large, maximum size, again, is something that we may need to change a bit. And this is what I want to do now. So I want now to say a spanning subdigraph is large. Now no longer of a finite digraph. If for every vertex there is an RV Erdős-Menger path system, so a path system for which there is such an orthogonal separator, and that of D, and for technical reasons minus RV, and L minus RV simultaneously. So, as again Erdős said, these path systems which have this orthogonal separation are the things witnessing the connectivity. And now we say a subdigraph is large if it still has the same witness for the connectivity. And removing this edge from R to V is something that we technically need to do. So this is nothing you really need to worry about. But of course, if there is an edge between RV, then this no separator. So there would be no separator according to my definition of Erdős-Menger separation, because R and V were not supposed to be in the separator. So that's just a technical restriction. Okay, and with this, with these definitions, Attila proved in 2019 the extension of Lovász's theorem. So for countable graphs, every countable digraph contains a large vertex flame, just large flame, and then Josh Erdy, me and Attila together, so just last year, about to be published soon, hopefully, extended Calvillo Vives statements. Now I need to be a bit more careful again, because now just saying every maximal flame in a digraph is large is a bit less meaningful, because maximal flames now do not need to exist. But a bit more careful, we can say every flame F in a digraph, countable digraph, can be extended to a large flame. Okay, so this is what we did. So this would be a good time to pause for questions.
Is it possible that there's some large flame which can be extended to an even larger large flame?
Yeah. That is possible, I think. So yeah, I think I'm not sure if it's possible in countable digraphs, but I can, I think, give you an interesting example. So here's our root R. Here we have a set X countable, and complete here. Here we have a set Y uncountable. Complete here. And let's again take a set Z countable. Complete here. Now each vertex here, of course, has now uncountable ingoing degree. But the connectivity, because of this separation, of course, is countable. So what we need to do is, for each vertex here, fix a countable set of ingoing edges. Actually, we can do that for each vertex here and keep all of those edges. And that will be a large flame. But of course, we could have chosen a slightly bigger countable set of edges as well, which still is countable, and have a large flame.
So I guess, do we need to keep all of the edges between the middle two sets?
That would be easiest. I don't think we need to, maybe.
I think we need to.
Maybe we need to, yeah.
And then.
But yeah, just throw away edges from here such that each vertex here has countably infinite degree, and we will be a large flame.
Right. Okay. Yeah, I think that's it.
I want to know whether it's really Erdős-Menger pass system when you take only the countably many edges from G to Y.
So this set will always be our Erdős-Menger separation.
Oh, that's a separate.
Yeah.
So doesn't matter which set of edges you take.
Yes.
I guess that's why.
That's why we want to keep all of them. Yes. Good point.
But yeah, I see now. We don't really care what we do with the final.
Yeah. Okay. More questions? Okay. Then let me give you a couple more definitions. and a couple of lemmas without a proof. So yeah, right. So how did Calvillo Vives prove his theorem? So he proved that whenever we have a flame, and for some vertex v other than the root, we add one of those maximum size path system from the root to the vertex, with the property that the difference of the number of edges in these path systems, which are not already on what we've constructed so far on the flame, if we add these, we keep the flame property. But this is now something that we cannot easily imitate. So, and if that's true, we just do this for every vertex and prove this theorem. But now we had this property. Okay, the number of edges not already on there is as small as possible. But now again we have infinite cardinalities to worry about. So what does that mean? There may not be such a minimal set that we can add and hope to keep the flame property. So we need to be a bit more tricky with this. And this is why we define so-called quasi-flames. But before I give you the definition of quasi-flames, let me define curly G of a digraph D and a vertex V as the set of subsets I of the ingoing edges of V in that subgraph, for which there is an RV path system covering I. Sorry? At this point, not an Erdős-Menger path system. Just we want to be reachable, and specifically for Rutger and anybody else who knows this definition, this is almost a gamma. That's why we call it G. Okay, so now using this definition, of course, we can restate the flame property as the whole set of ingoing edges is in this set. But now let's define what we are actually after. So if we have a digraph G, which is a subdigraph of D, then D is a G quasi-flame if for each vertex, again let this be spanning, for every vertex other than the root, and for every subset of the ingoing edges of V, if I without the ingoing edges of the fixed graph G that we had is finite, then I should be in this curly G. So then we can find a path system with this as its terminal edges.
So I is a Oh, in D and
In
I
D,
see.
yes.
Ah.
So the idea is we plug in our flame here as G that we want to extend, and yeah, so the quasi-flame property, which is easier to guarantee in the step than the flame property. Now the idea is we try to mimic Calvillo-Vives' proof. Adding this path system keeps now the quasi-flame property in some sense. So I will be more precise in a bit. Okay. So now I run through 4 lemmas, which may be of variable degree of believability. Okay, so first lemma is if F in D is a flame, then there is a Z such that F is in Z is in D. Z is an F quasi-flame. And now the most important thing, such that whenever L subset Z is large with respect to Z, then L is large with respect to D. So the idea of this lemma, without loss of generality, we can say that the digraph we're starting with is already a quasi-flame. Okay. Now, I guess the really key lemma, which is, I guess, the least believable and the hardest to prove. So half of the paper is devoted to prove this single lemma here. So if D is countable, so for this lemma we need it, and G is D is G quasi-flame for some G, and take some vertex other than the root. Then there is a set I star, which is the set of final edges of one of those RV path systems, such that when from D we delete all the ingoing edges of V which are not in the set I, this is still G quasi-flame. So similar to the Calvillo-Vives idea, we wanted to keep the flame property Well, here we kind of work our way backwards and choosing so basically this set I, of course, comes with a path system, and then throwing all the other ingoing edges away so that we will get the flame property for that vertex, keeps us the quasi-flame property. This will be the key idea in the main proof. Okay, our third lemma is a bit easier, and it's more a slight technical thing. But if we have L as a subset of D, and L is now what I call V large, and this means has the largeness property for the vertex V. For all V where V is the vertex such that the ingoing edges of D of V, of L of V, is a strict subset of the ingoing edges of D of V. So if we are only large for those vertices which have strictly fewer edges, then L is large. So we only need to check largeness for the vertices where we don't have all the ingoing edges. And lastly, if L is V large, then for all I in G of V, there is a path system P and this now is an RV Erdős-Menger path system, and of L and D simultaneously. Okay, these are the four lemmas. And if you believe them, I now present you a proof. And after that, we may have a couple of minutes to look into some of these. Any questions so far?
Oh, right. This isn't about flames, it's about largeness.
This is only about largeness, and this is only about largeness. And the other, so we have two about flame-ish things, so about the quasi-flame-ish, and two about largeness. Okay, so proof of theorem. Okay, so first what we do is we enumerate all the vertices other than the root, which we can do because we assumed countability in the main theorem. I wiped the main theorem away, but we did do that. And now lemma 1 says we may assume D is an F quasi-flame. So F was the flame that we want to enlarge, or extend to a large flame, I should say. So now we do a recursive construction. So G naught is just F, and L naught is just D. And now we've recursively find a path system Pn plus 1. Which should be an Erdős-Menger path system for D, for D and Ln simultaneously. Right, D and Ln simultaneously. Then we define Gn plus 1 as Gn union this path system. Then we define Ln plus 1 as Ln, again, where we delete all the ingoing edges in D of Vn. Oh, of course, this is from R to Vn. We delete all of these, but the ingoing edges in Gn plus 1 of Vn. And we want to do it in such a way that Ln is Gn quasi-flame. So this is the property that we need to guarantee throughout the construction. It's a newly defined thing, yes. So if we have all of that, then so the GNs are increasing sequences of spanning subgraphs. The Lns are decreasing sequences of spanning subgraphs, and they converge both to some specific subgraph, namely the union of all of these equals the intersection of all of these, and that will be a large flame. So all these path systems are in there, which are Erdős-Menger path systems of D, so they do witness the largeness. And by the definition of the L, we've thrown all the other edges, ingoing edges away, so we will be a flame. Yeah, that's. I mean, if we would delete edges which are not in there, then it doesn't matter. But yeah, Ln would be probably more precise to write. Okay, and now our lemmas actually allow us to do that. So, so we used lemma 1 already to say D is a quasi-flame. Now we can use lemma 2. Oh, it doesn't have a number. And for this new vertex Vn plus 1 that we are looking at, we find this set I star, so that doing this restriction keeps the quasi-flame property, which guarantees us this such that basically. Okay, let me come back to that. No, so first, this lemma 2 guarantees us that that Ln plus 1 will be a Gn quasi-flame, not yet a Gn plus 1 quasi-flame. Then we will apply lemma 3 and note that that Ln plus 1 now is still large. So again, largeness. So this lemma says we only need to check largeness at the vertices where we modify a bit, and the only vertex we are modifying is Vn, and the existence of the path system guarantees us largeness for that vertex. So keeping largeness is fine, meaning we can apply lemma 4 for this set I star now from lemma 2. We find the Erdős-Menger path system of L and D simultaneously. So this is the path system we found. Then we define these two. And then all that is left to check. So we know Ln plus 1 is a Gn quasi-flame, and we need to show it's a Gn plus 1 quasi-flame. And to do that, we again notice that for the new vertex that we just added, we have the path system which witnesses that we are even have the flame property, not just the quasi-flame property. And for all the other vertices, we can observe that adding this path system, so all these path systems are, again, all these paths are internally disjoint. So for each other vertex other than Vn, we added only at most one edge to each other vertex of the graph from Gn compared to Gn plus 1. And the quasi-flame property now is trivially preserved because it already said if we only need to check that we can add finitely many edges. But now we did add one, so we need to add this all the time. But then adding finitely more, of course, keeps the quasi-flame property. And this is the proof modulo all the lemmas. Questions so far? Then let me mention open questions. So, of course, we would like to drop countability here. So it seemed to be really crucial in lemma 2 so far. So and here we also used the enumeration of these vertices. So it's not clear how to do that. Although maybe for graphs of size Aleph 1, maybe elementary submodel argument can maybe just work, and using this big set theoretic tool may be enough to guarantee us for those graphs. But it seems also not clear how one could push that further. And maybe the more interesting question would be the edge version of all of this, as Casey originally asked in the beginning. So what Lovász and Calvillo-Vives actually proved was an edge connectivity version of all of this. So instead of Erdős-Menger vertex path systems. We look at, instead of internally disjoint, we are only looking at edge disjoint, which maybe is the more natural setting for all of this, and so on. But there are a couple of key steps in this idea which just fail. So this whole quasi-flame approach seems doomed for edge flames. In that, so for example, when we here proved the quasi-flameness, we modify each other vertex only by deleting at most one ingoing edge. Now that's no longer true if we are just looking at edge disjoint. So there's a big question mark on how to do this. But if any of you are interested in working on this, especially the edge version, am very interested in. And if you want to know some details about any of these lemmas, come to me and I may be able to tell you some ideas over tea or something. That's it.
For the edge version, I was curious because about the line graphs. So normally for finite graphs, we use line graphs to convert the theorem on vertex version to edge versions.
Mm-hmm.
So if I want to prove something for edge version, can I just take the line graph on and then see what happens? Does it fail? Or?
So I don't really see how. So yeah, I'm actually not sure how the standard derivation from Menger's theorem goes from the vertex version to the edge version, but I don't think it's just a line graph thing. Yeah.
Similar things for metro?
I mean, that may be something to think about, but it's at the moment a bit unclear. So, so with directed graphs and matroids, there's of course always the question on what really to look at. So in some sense, there is some amount of matroid theory hiding here with the gamoids, which I'm hinted at. But again, these may fail to be matroids, and that's why we don't call them gamoids in that case. So for specific reasons. So I'm not quite sure what the right questions to ask would be, but there may be questions. Yep.
Is there any hope that you could do like so instead of saying the graph is countable, if all the vertices have countable degree or something like this? Countable max degree?
That is a good question. So at least some of the proof would need to be modified because this enumeration argument would no longer work. But yeah, but maybe something like lemma 2 could be modified to that regard. I think that may be something to look at. Yeah. But yeah, so I mean, there still is work to do something because this proof wouldn't work.